Welcome to Ask and Learn.
Okay, a freezer has a coefficient of performance of 2.4. It's to convert 1.8 kilograms of water at 25 C to 1.8 of ice at minus 1.5 in 1 hour. What amount of heat must be removed from the water at 25 C to convert it to ice at minus 5 degrees C? Okay, so, and then I'll read the second part, I guess. How much electrical energy is consumed by the freezer in this hour? And see how much wasted heat is delivered to the room in which the freezer sits. Okay, so I went ahead and wrote down the givens, the coefficient of performance K, 2.4, and I wrote down some givens that will need, because this is a heat transfer problem, we'll need heat capacity. So, and the two substances we're dealing with are water and ice, and they have different heat capacities, even though it's the same molecule. In addition to the heat capacities, we also have this latent heat of fusion. So it costs energy, or I guess energy is released when ice is stays at like 0 degrees but goes from water to ice. Excuse me, when water stays at 0 and goes from water to ice. And then finally, I want to just note that the change in temperature of the ice. So once, maybe it's better to read water first. The change in temperature of the water is minus 25 degrees C because we start at 25 and we want to take it to 0. So we need to figure out how much heat is lost in that process. And then we'll do the phase transition, figure out how much heat is lost in that process. But after that, we need the how much the temperature of the ice is changing. So it's going below freezing. So it's going minus 5 degrees C. So that'll come up, and maybe the context will be more clear when I start the problem. And I also want to note that minus 5 degrees C is minus 5K if you're talking about temperature differences, and the same for the minus 25 C and K. Okay, great. So now that we have all the givens written down, part A, we want to get the heat lost. So that is just going to be the heat lost due to first get the water down. Oh, did I write down the mass? Oops, I didn't. All right, let me add that to the end. 1.8 kilograms. Okay. And so that's, so first we need to cool the water down. So to make it into ice. So mass of water, C of water, delta T of water. Okay, now we've made the water into ice, then how much more heat is released when you convert that ice or water to fully to ice. Like you've gotten the water all the way down to 0, and now your goal is to convert it all to ice. And so you're going to lose some heat during that phase transition. So that's just minus LF times M. And then I guess I'll use just like the same, they're all the same mass, so I don't really need to put a subscript on the mass. So I'll just go ahead and erase this W here. Okay, and where's my pen? There it is. Great, and then the last step is just converting all that, or taking all that ice that you've just created and bringing it to even colder than 0 degrees. So that's just going to be the same idea as cooling the water, but now we have to use C of the ice times delta T of the ice. Great, and so I tried to label everything, but basically you just need to plug in all the numbers from the left into the formula from the right. So that's 1.8 times 4190 joules per kilograms times minus 5 minus, and this should be a negative term, minus 3.34 10 to the 5 times the mass 1.8 minus the mass times 1, which is 1.8 times C of the ice, this 2010 joules per kilogram Kelvin, delta T of the ice minus 5 Kelvin. And if you do that, hopefully you'll get what I got, which is minus 8.08 times 10 to the 5 joules. And so that tells us our Q cold. So I'll just go ahead and label that as Q cold. And then that's going to be kind of a given for the next couple problems. So I'm going to just go ahead and review the problem again. So yeah, and then how much energy is consumed by the freezer during this hour. So for that, we want to find the work done, and the work done is going to be this Q cold over K. And if you plug in this QK magnitudes, so you plug in this 8.08, no negative because we do magnitudes divided by K, you should get this 2.4. You should get 3.37 times 10 to the 5th joules. And for part C, you want to get Q hot. It's equal to the work plus Q cold. And then if you add in the work and Q cold, then it's 1.14 times 10 to the 6th joules. And just to note, they kind of talked about doing all this during an hour. That wasn't really necessarily relevant. Nothing really had to do with time. They asked for powers, and you might divide these energies by then you might divide by 60 seconds.